everyone, I'm Eric, and today we'll be doing a pretty short lesson on, number theory. Now, last time we talked about primes. This time we are going to talk about counting primes. Now, we are not very extraordinarily familiar with primes, but we are with even numbers. Like even numbers, odd numbers, 2, 4, 8, 10. I don't even need to list them. And 6. Oops. Well, we're going to ask how many even numbers are there. Well, there are infinite even numbers, and we're done. It's too broad of a definition, so we're going to try to look at something closer. So we're going to go from just answering infinitely. We're going to go from that to counting even numbers, and we're going to create a list called EX, which is basically the number of even numbers between 1 and x inclusive. So, for example, E3, well, that's just 1, because A2, E4, 2 and 4, and E100, there are 50, 2, 4, 6, 8, 10, all the way to 100. E101 is also 50. Now we can see that, now let's observe EX over X. We can't say that it's always 1 over 2 in cases of E4 and E100. There are always other cases. For example, E3, which is 1 over 3, which is definitely not 1/2. But what we can say is that when x is close to infinity, then EX over X will be close to 1 over 2. And that's probably right, because 50 over 101 is way closer to 1/2 than 1 over 3, isn't it? Well, we can actually use the same train of thought and do this with primes. So we are also going to create a function, pi x, not a function, a list, pi x. Now note that we used pi here, and actually pi in Greek letters, how they used pi, it has no relation with the number 3.1415965. It had absolutely no relation. We just put a Greek letter to represent 3.1415, and that's it. So we're going to create a list pi x, which is the number of x's between 1 and x inclusive. When x is 10, there are 4 primes, 125 primes. We'll check out on pi x over x, and we find 0.4, 0.25, 0.168, and these humongous numbers I'm not going to read. It doesn't seem to have any pattern. Well, what about x over ln x? Now, what is ln x? ln x is log ex, and I do not know why I picked the space over here. And what is log? And what is e? Well, e is a number, 2.717, that stuff. And what is log? Log is basically like modulo in exponent. So for example, log 2, 4. Well, 2 to the second power is 4, so it's 2. It's kind of like modulo. Basically the same concept, but in exponents. So what if they just gave you a log, like log 100? Then how are you supposed to do that? Well, if they don't give you any number underneath it, it basically means log 10. So log 100 with nothing under the log is basically 2. And log 10 something, you can also write it as log. And log e something You can write it as ln. So that's what ln is for. So x over ln x. 4 point something, 21 point something, 144 over something, 1,000 something, 72,000 something, and oh my gosh, this number is big. Well, it doesn't seem to have any pattern overall. These two, they both doesn't have any pattern seemingly. But if we use pi x over ln x, it sounds quite a bit I just can't get my brain over it. It's a tongue twister. We find that it will be approximately equal to 1 when x is approximately equal to infinity. And, well, we have the prime number theorem. One that we just made up. Well, not we made up. Someone definitely made it up before us. So, when x is close to infinity, pi x over ln x is, well, close to 1. And we can't prove it right now because, yeah, we have to go through some calculus. So we're just going to back off for now. We're probably going to come back to it later. Now, primes are a very interesting topic in number theory, and there had been a lot of debate and theorem making around primes. Many of these theorems had been proved, but quite a few of them are still standing there, non-proved. So, for example, the Goldbach conjecture: every even number with n greater or equal to 4 is a sum of two primes. For example, 4 itself, 2 plus 2, 3 plus 3, 6. And the closest we've ever come to proving this is the sum of 1 prime and 2 other numbers, but not just 2 primes. So it's actually very hard to prove. Also, there are the twin primes conjecture, which states that there are infinitely many prime numbers, p, such that p plus 2 is also a prime. For example, 3 and 5. So there are twin primes. And the n squared plus 1 conjecture. I guess the name can definitely use some improvements, but it basically states that there are infinitely many primes in the form of n squared plus 1. What does that mean? Well, 5, 2 squared plus 1, because that's 4 plus 1. What about 4 squared plus 1? That's 17, also prime. So are there infinitely many primes with this shape? This form. So that's actually all that we're going to cover today. And as I've said, it's quite a short lesson covering a new train of thought and counting even numbers and using the exact same train of thought to prime numbers. And note that this is ex over x, but meanwhile, this is pi x over ln x, which is a lot more complicated. So how do you find those? Well, we just look at many of these with the same train of thought, and we basically have, I just know it. It just comes to your brain. So if you've seen too much of these, then it just comes to your brain, and that's what Fermat probably did. And we had covered quite a few, 3 conjectures, namely the Goldbach conjecture, the twin primes conjecture, and the n squared plus 1 conjecture, which its name could use some improvement on. These 3 conjectures had not been proved until today, and yes, they seem very simple, but things that seem simple are, they can be extraordinarily hard. So that will be all that we'll be covering today, and see you guys next time.